All right, who has questions? No questions. Okay. I don't know where we left off. So what we're going to do here is we're going to leaf through some of these problems. And when you see one you like, we'll do it. So let me change my switch screen or my share screen. And you're going to have to give me some sort of a indication that you'd like to do this problem. Let me see now. I need to use more of the screen. Okay, so
I remember you doing this on the last time we did the.
Yeah, I'm gonna skip a few of these. Do you remember what we left off on?
You can probably stop the.
Did we do any precipitation reactions?
No.
Okay, so this is the last time we're going to be lecturing on this particular chapter. So I'm going to do a smattering of these. We don't want to do all of them, although all of them have pretty much been done on other videos. So let's go ahead and get started. Predict the precipitation reactions. So for this, you need to know what the precipitation rules are. And so I'm not going to go through those right now because they're in the lectures, they're in the book, and so forth and so on. We're just going to apply them. So in this case here, aqueous means that this is dissolved, and dissolved means that the ions are actually not together anymore. They're surrounded by water molecules. So this aqueous actually means this. And the same thing here. So if you don't recognize the ions that these are made out of, you're going to be in a world of hurt. Okay, so we have to balance the equation and write the net ionic. So in these precipitation reactions, you take a look at all of the ions and you ask yourself, is it an always soluble ion? Because if it is, it's not going to be part of the precipitate. So these are always soluble. They're not going to be part of the precipitate. So that only leaves these two. Now you notice this is a +2 charge and this is a -1 charge. The precipitate is of course going to be an ionic compound. And it's going to be written as a neutral compound. So we need 2 bromines. And I should be saying 2 bromides for 1 of the leads. So this will be the solid. And this is what's left over. Now to balance this, you can see that we have 1 lead, 2 nitrates, 2 nitrates, 1 potassium, 2 bromides, 1 bromide and 2 bromides. That's not going to work. We're going to need 2 of these. But if I put a 2 in front of there, that also means I need a 2 in front of the K. And that means I'm going to need 2 Ks over here. And now this is balanced. So this is the overall reaction. And so if we wanted to write the overall reaction more simply than what we've written above, it would look like this. So that's the reaction. So what does the net reaction look like? The net reaction, if we look at all of this stuff written above, we exclude the things that are identical before the arrow and after the arrow. So these things are identical. And these things are identical. These things that are identical are called spectator ions. And they're excluded from the net. So the net would end up being Pb 2 plus aqueous plus 2Br minus aqueous gives you Pb Br2 solid. And there's your net. Okay, so I'm going to let you guys do B and C on your own. Any questions on this one? Don't be shy. Okay, well, I'm going to go to the next question.
Put it back there for 1 second, please.
This one right here.
Yeah, just I'm on the bottom. I'm just writing up the bottom with.
Okay, let me move it all up there just a little bit.
Thank you.
You bet. Okay, so this next one, write a balanced equation for the ionization of perchloric acid in water. So this is the formula for perchloric acid. And we want to show how it ionizes in water. So we could actually answer this two ways, and I believe that this is the way they want us to do it. So we're showing it reacting with water, and when it ionizes, it loses an H plus, and that H plus adds to water. So if you have an H plus add to water, you're going to have 3 hydrogens. And because water is neutral and H plus has a +1 charge, you'll have H3O plus, and this is called the hydronium ion. This, because it loses an H plus, becomes just ClO4, but also it has to have a negative charge. So this is one way to write the balanced equation for the ionization of perchloric acid in water. And this would be the Bronsted-Lowry way of doing it. And there, of course, is another way to do this, and that's this way. And this is the Arrhenius way of doing it, where for an Arrhenius acid, we say it makes protons in water. Any questions on that one? Okay, we're going to move forward then. All right, phosphoric acid can supply 1, 2, or 3 hydronium ions in aqueous solution. Write balanced equations to show the successive loss of hydrogen atoms. So this is the formula for phosphoric acid. It's a weak acid, so when it reacts with water, it does so reversibly. So I'm going to have 2 arrows here. So it's going to, with water, make the hydronium ion. So here, one of these hydrogens transfers to water, but it's not a hydrogen per se, it's a hydrogen ion. So the hydrogen ion makes the water positively charged in addition to having an additional hydrogen. So what happens to this guy? Well, there's one less hydrogen, H2, PO4, and that's aqueous. And since this guy loses an H plus, it becomes negatively charged. So you'll notice that if you look before and after, we have the same number of hydrogens, same number of phosphorus, same number of oxygens, and the same charge. 0 plus 0 is 0, plus 1 and -1 is 0. Now this guy is also an acid. And it can react with water. And it's going to make another hydronium ion. So I'm going to give you a moment to write that down and to figure out what this thing is that it also makes. When you think you know what that is, give me a thumbs up. Okay, so because this loses a hydrogen, it's going to become HPO4. And we know that the charges have to add up to be the same on each side. -1 and 0 is -1. So to have a -1 on this side, that's going to have to be a -2. That's an acid. So this one, I'm going to let you finish on your own, and we're going to go ahead and move on. Okay. Any questions on this one? All right. Write a balanced reaction for the reaction of sulfur trioxide and gas with water. What they're trying to get you to understand are two things: that if you have a metal oxide and water, you're going to make a base. And if you have a non-metal oxide and water, you're going to make an acid. So let's see. Common examples of this would be for a metal oxide, you might have, let's see, sodium oxide plus water, and you make sodium hydroxide. A great example of a non-metal oxide in water is carbon dioxide. If you get enough carbon dioxide to dissolve in water, it will make carbonic acid. So in this particular problem, they're asking us for the reaction of sulfur trioxide with water. And in general, what you're going to do is you're simply going to look at all the formula here and write them down right here, starting with hydrogen. 2 hydrogens, 1 sulfur, 4 oxygens. So sulfur trioxide and water mixes to make sulfuric acid. And this, back in the day, was stuff called acid rain. And it actually dissolves statues, which are made out of carbonates. And the reason you get these compounds produced in the atmosphere is because you burn coal. Coal, we know, is carbon, but coal comes from living organisms, mostly plants. They say that, you know, the fuel you're burning in your car is some Tyrannosaurus Rex. Maybe, but probably most of the coal that we burn is from plants. There's a lot more plant material in the past than there was animal material, kind of like today. So what are plants made out of? Well, they're made out of living tissue, which has carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, all sorts of nonmetals as well as metals in there. The nonmetals, when they react with oxygen, they form gaseous compounds. The metals, when they react with oxygen, they tend to form oxides that are solids. So the ash you have left over from burning a piece of wood are mostly metal oxides, whereas the non-metal oxides turn into gases. So these gases react with rain and you get acid rain. So how do you prevent this from occurring? And the answer is simple. When you have a coal plant and you burn the coal, rather than let the gases just escape to the atmosphere, you just kind of run it through some water. And when you run it through some water, you're going to make this sulfuric acid, and you keep that from ever going out into the atmosphere. So acid rain used to be a great problem back in the 70s. Everyone recognized what the issue was, and the simple solution: run your gases through a scrubber, as they would call it, and remove the gaseous non-metal oxides. Now, of these two compounds here, which one is, of course, the worst abuse, if you will, the worst thing for acid rain? H2CO3 or H2SO4? And the answer is H2SO4, because that's a strong acid. H2CO3, carbonic acid, is a weak acid. So any questions on 34? Speak up if you have any. All right, then. 36. Complete and balanced equations for the following acid-base reactions. Whenever you're balancing acid-base reactions, you want to count H pluses in the acid, and you want to count OH minus in the base. And you want to adjust the coefficients so that you have the same amount. So for A, you've got 3 hydrogens. And for KOH, you've got 1 hydroxide. So these do not equal. How do we get them to be equal? And the answer is put a 3 right here, and now we have 3 hydroxides. Now, when you do get the same number of hydroxides and hydrogens, you're going to make that many waters. So here, if we have 3 and 3, we're going to make 3H2O. And then you just take the remaining ions and put them together. I have 3 potassium ions. So I'm going to try that. And then I have 1 phosphate ion. And there's your reaction. Now, for these leftover ions, it usually works out where the formula is just perfect. But if you did get something like this, what would you do with that? And the answer is you'd write it this way. Because 6 and 2 can be simplified to 3 and 1. Okay, so for B, we have 2 hydrogens. And we have 2 hydroxides. So this is a match made in heaven. Now, when you have 2 and 2, how many waters do you make? 2. What are the leftover ions? 1 calcium and 1, this is called an oxalate. And this is the way this reaction would look. Now, we're supposed to also name the reactants and products. So Let's do that. This is phosphoric acid. This is potassium hydroxide. This is dihydrogen monoxide. And this is potassium phosphate. This down here is called oxalic acid. This is called calcium hydroxide. This one we've already named dihydrogen monoxide, and this is called calcium oxalate. Are there any questions about this one? Okay, then we're going to go on. So write a balanced equation for the reaction of aluminum hydroxide and sulfuric acid. So for aluminum hydroxide, you need to know that aluminum is a +3 and hydroxide is a -1. So the formula is AlOH3. That's going to be a solid because hydroxides are not soluble. And you're going to react it with sulfuric acid. So you know that sulfate is SO4 2-. So the acid, sulfuric acid, is H2SO4. So how many hydroxides? 3. How many protons? 2. Not a match made in heaven. So what are we going to do? Well, the answer is let's put a 2 here, and then we'll have 6 hydroxides. And let's put a 3 here, and then we'll have 6 hydrogens. When you have an even odd like this, 3 and 2, usually you multiply those together and shoot for what they come out to multiply to. So if we have 6 hydroxides and 6 H's, how many waters do we make? Well, you need 2 hands for it. 6, right? 6. Now, how many aluminums left over? 2. How many sulfates left over? 3. Sulfates in general are soluble, so this one is going to be aqueous. Okay, let's move on. 40 says refer to the book. We're going to skip. Write 2 chemical equations, one in which this dihydrogen phosphate is a Bronsted acid with the carbonate ion CO3 2-. They don't say anything about the state, so I'm going to leave that off. So the definition of a Bronsted acid is one that is a proton donor. So this guy's going to donate a proton, which means it's going to lose a proton. When it loses a proton, it becomes HPO4 -2. So if this guy is going to lose a proton because it's a Bronsted-Lowry acid, then this is the Bronsted-Lowry base, which means it's going to gain a proton or accept one. So how do we write this when it's accepted a proton? HCO3 -1. So this guy turns into that guy, and this guy turns into that guy. So the second reaction, we're looking at HPO4 -2, and that's our Bronsted-Lowry base. And it's reacting with CH3CO2H, and this is our Bronsted-Lowry acid. So what does our acid turn into? Well, it's going to give up an H, turns out to be that one. And when it gives up that H plus, it becomes CH3CO2 minus, the acetate ion. This guy, on the other hand, is going to pick up that hydrogen. So 2. And it's not a hydrogen it's picking up, it's a hydrogen ion. So this is going to become less negative, and there you go. Any questions about this one? So I do want to talk for a moment about these. This is called a conjugate pair. And you can see that the conjugate pairs look very similar to one another. They differ by 1 H plus. And for the conjugate pair, one of them is always a Bronsted-Lowry acid. The other one's a Bronsted-Lowry base. So if this is a Bronsted-Lowry base, what does that make this? That's right, a Bronsted-Lowry acid. So this is another conjugate pair. They differ by 1 hydrogen. And when you're looking at pairs, how do you know which one is the base and which one's the acid? And the answer is really easy. The one with more hydrogens is the acid. So between these two, H2 or more hydrogens, that's the acid. Between these two, well, there are no hydrogens in CO3, so this one that I'm tapping is the acid. If we go down below here, which one has more hydrogens? The one on the left, it's the acid. So what's the other side? A Bronsted-Lowry base. And if we look at these two, which one has more hydrogens? Well, the one on the right, so it's the Bronsted-Lowry acid. Okay? All right. Balance the following, then write the net ionic reaction. So I'm going to do this for one of them, and I'm going to let you guys go to town on the rest. And I'll just start with this one. So when you're trying to get to the net ionic reaction, you want to write these out as they are in the reaction. And I'll show you what I mean by that in just a moment. So here's the reaction written out again. I'm just going to balance it to begin with. 1 zinc, 1 zinc, 1 hydrogen, 2 hydrogens. So I want to put a 2 here. Now I've got 2 hydrogens, 2 hydrogens, 2 chlorides or 2 chlorines and 2 chlorides. So they match. So what do these states mean about how these exist? Well, the zinc is just a piece of solid zinc. Here, this is a strong acid, and because it's aqueous, it means that it has come apart and actually formed 2 H pluses and 2 chloride ions. So this is more of the Arrhenius definition, where these hydrogens we think of as just being H pluses. What about the H2? Well, we just bring that down. The only time we think about splitting things apart is when it says aqueous. So this one is aqueous, so we're going to say we have zinc ions that are aqueous and chloride ions that are aqueous. So this would be the total ionic equation, where this is the balanced reaction. And how do we get the net? Well, to get the net, you do the following. You include all solids, liquids, and gases. So if we look above, we see that zinc is a solid. I'm going to include that. I'm leaving a little space here. No other solids here, no other liquids, and no other gases. But over here, I have a gas, so I'm going to include that. And then do not include ions that are aqueous that are the same on both sides. Those are called spectator ions. So is there anything on the left of the arrow that's identical to the right? Well, zinc solid, zinc aqueous, they're not identical. 2 hydrogen ions, 2 hydrogen atoms, they're not identical. 2 chloride ions that are aqueous and 2 chloride ions that are aqueous, these are identical, and these are spectator ions. So you do not include those. So that means we have to include the 2 H pluses, and we have to include the zinc. And that's how you get your net. So get your balanced reaction, get the ions, bring down solids, liquids, and gases, and anything else that's not a spectator. That's all there is to it. So you do the same for all of these. So which of these things are we going to bring down automatically into the net? Well, this because it's a solid, and this because it's a liquid. Which things here are going to end up in the net automatically? This because it's a solid, this because it's a liquid, and this is because it's a gas. And here, what things are going to end up automatically in the net? This because it's a solid. Okay, so give those a practice, see what you can do with them. And we're going to move to the next one. .46, refer to the book. No, thank you. 48, write balanced net ionic equations for the following. So I'll do one of these and you can do the other. Aqueous solutions of silver nitrate. So we know that silver is a +1. We know that nitrate is a -1. So the formula for silver nitrate is AgNO3, and they even tell us it's aqueous. Now we're going to react that with sodium iodide, which is also aqueous. Sodium is a +1. Iodide is a -1, so you're going to write NaI for sodium iodide. Now, we're trying to figure out what type of reaction this is, and our choices are acid-base, redox, gas forming, or precipitation. For an acid base, you need an acid and a base. We have neither here. For redox, you're usually looking for a pure element in a neutral state, and I don't see that there. For a gas forming reaction, you're usually looking for carbonate or sulfite, and I don't see those here. So this must be a precipitation reaction. So to figure out what happens here, we separate the ions. And when I say we separate the ions, above where I have this silver nitrate, they are separated, but we don't write them that way for ease. It's easier to write this than it is to write this below. So these are separated. When I say write the ions and separate them, I mean really make it obvious that they are not bonded together. Okay, now if this is a precipitation reaction, we have to figure out which two of these ions come together and form a solid. And it's really simple. In this case, sodium ion never forms a solid in water, and nitrate ion never forms a solid in water. So it can't be these two ions as part of the solid, which means it's got to be the silver and the iodide. So what is the formula if it's a +1 and a -1? And the answer is one of each. And it forms a solid. And then you got your sodium left over and your nitrate left over. So to write the net, we include all solids, all liquids, all gases. So there's the solid. The things that we don't include are ions that are the same on both sides, like this nitrate and this sodium. They are the same on both sides, so I will include the silver ion that is aqueous, and I will include the iodide ion that is aqueous, and there's the net. Any questions? Are you alive? Okay, we'll move on. I don't believe you, Greg. Okay, the mineral rhodochrosite is magnesium 2 carbonate. Write an overall balanced equation for the reaction of this mineral with hydrochloric acid and name the products. So this is a gas forming reaction because it's got the carbonate and you're reacting it with acid. So manganese 2 is this, carbonate is this. So that makes manganese 2 carbonate that. Now, carbonates in general are not water soluble unless it's combined with sodium or potassium or ammonium. Hydrochloric acid is HCl, and you can buy that aqueous. All right. So
Is manganese, isn't that Mg?
no, that's magnesium.
Oh, okay, sorry.
Yeah, manganese with the N is a Mn, and that's kind of the hint. Oh man, no, right? Whereas magnesium doesn't have that N to begin with. But yeah, those are often confused. It's very common to confuse those. Okay, so here the deal is to balance these reactions, we have to understand that we need 2 hydrogens from the acid to react with a carbonate from the base, or 1 hydrogen from the acid to react with a hydrogen carbonate from the base. So what do these two things have in common? And the answer is they both make something with 2 hydrogens, 1 carbon, and 3 oxygens. Now, this is called carbonic acid. It's pretty unstable in water. And what happens to it immediately after it forms is this. You get H2O and CO2. So again, the key to balancing these is to make sure you get H2CO3. So let's look above. I have my carbonate, that's my CO3 part, but I only have 1 hydrogen. So what do we need to do so that we can get 2 hydrogens? Put a 2 there. Now that we have exactly 2 hydrogens and exactly 1 carbonate, we will get exactly 1 H2O and 1 CO2. The H2O is a liquid. The CO2 is a gas. But this doesn't explain what happens to the manganese or to the chlorides. So if we think about it, manganese is a cation, the chlorides are anions, they make an ionic compound. And then we have to decide whether this is dissolved or not. And the rule for chlorides is that they are soluble unless mixed with something like silver or lead. So there's your balanced reaction. Gas forming. Okay. I'm going to move on. So this is another gas forming reaction. This is sodium sulfite. Not sulfate, but sulfite because it's SO3. And this is acetic acid. Now, the key to these reactions is that you have two hydrogens react with a sulfite, and you're going to get H2SO3, which splits apart into H2O and SO2. Does this look similar to the previous one? And it should, because here we have SO3 instead of CO3. It's still a 2 minus. This looks like H2CO3, only it's an S, and you get H2O and SO2 instead of CO2. Now, we talked before about these non-metal oxides, they're gases. So this is another gas forming reaction. And here, to get two hydrogens, these are the hydrogens that react from the acetic acid. So I need to put a 2 here. So what's left over? 2 sodiums. So 2 sodiums and 2 acetates. Now, if we look at that, does that look like a good formula for an ionic compound? And the answer is no, because it can be simplified. But how do we account for having 2 of these and 2 of these? And the answer is you write a 2 in front. And of course, it's aqueous because of the sodium ion or the acetate ion. It's your choice. And so if we name everything, this is sodium sulfite. This is acetic acid. This is dihydrogen monoxide. This is sulfur dioxide. And this is sodium acetate. Okay, so another common gas forming reaction that is similar to CO3 2 minus. Okay, let's put that over here. Now, this is a topic that we want to get through tonight. How do you determine the oxidation number of elements in ions or compounds? There's a few rules you need to be able to use. Rule number 1. Rule number 1. The sum of, so take a look at this. ON means oxidation number. I don't want to have to write that out again and again and again. So that's something that you need to know is ON is oxidation number. So I'm going to give rule number one is that every atom in a substance gets an oxidation number. Every atom has an ON. 2, when you sum the oxidation numbers, it equals the charge. 3, for monoatomic ions, the oxidation number is equal to the charge. 4, and this is in order of what's important. 4, in compounds, F is -1, oxygen or hydrogen is +1, oxygen is -2, and chlorine is -1. So in that order. So those are the rules. Let's apply them to these right here. So how many oxidation numbers do we have in A? We have 7. We have a phosphorus, a fluorine, a fluorine, a fluorine, a fluorine, a fluorine, and one more fluorine. When we add these oxidation numbers all together, so this is number 2, when we add up all these oxidations, it has to equal a -1. So when we look at these for monatomic ions, well, there are no ions here. In fact, none of these have ions, so we can skip rule number 3. So number 4, we apply fluorine is a -1. So this becomes P -6 is -1. Because if each of these fluorines is a -1, then 6 of them would mean -6. So by default, then phosphorus has to be +5. So the way we would write this out to help us later on is we would write the following: +5 and -1 each. Do not write this because that's going to screw you up. We want to know the oxidation number on each atom, not the total. Okay, let's apply this to B. Two hydrogens, 1 arsenic, and 4 oxygens. The total has to equal -1. Hydrogens are +1s. Oxygens are -2s. So if we add up all these -2s and all these +1s, we get -6, and the arsenic is +5. So the way we would want to write this out is +1 each, +5, and -2 each. Okay, so I'm going to let you guys do this O2 plus. Once you've assigned oxidation numbers, give me a little thumbs up or something. Have you got it, Greg? Okay, so we know that the U plus the O should be plus 2. We know that the oxygen is a minus 2. So we get that the U is a plus 4. So we got plus 4 and minus 2. So that's how you assign oxidation numbers. I'll let you guys practice some more with these. What we want to do is we're going to skip this one for right now. Here we want to decide what got oxidized and what got reduced. So this is going to allow us to get more practice assigning oxidation numbers. And it'll give us practice deciding how to use them. So I'm going to write this out again, Cr2O7 minus. I'm not going to worry about the state. Plus 3, 10, 2 plus 14 H3O pluses, 2 Cr 3 pluses, 3 SN 4 pluses, and 21 H2Os. So our first rule is if we see a neutral element, it gets a 0. Oh, I forgot that rule. So we're going to make this 3, 4, and 5 neutral elements have an oxidation number equal to 0. So add that to your list, rule number 3. Okay, so let's go back to this now. No neutral elements. I do see elements, but they're not neutral. So rule number 4 is monatomic ions, the oxidation number is equal to the charge. So even though there's 3 of these, each one is a monatomic ion. So SN 2 plus is a monoatomic ion. So what is the oxidation number on that 10? Plus 2. Any other monoatomic ions? Oh, right there. What's the oxidation number on that? Plus 3. Oh, and here's another one. Plus 4. Okay, so we've applied the monatomic rule. Now we apply the FHON or FHOCl rule. There's no fluorines, but we do have hydrogens and oxygens. Hydrogens go first. So these are plus 1. These are plus 1. What does oxygen have to be so that this ends up being a plus and it's a negative 2? And here it's a negative 2. What is each oxygen here? A negative 2. So here I'm not doing all the algebra, but I'm just kind of doing this in my head. I know that each oxygen is a minus 2 and there's 7 of them. So that's minus 14. So what does this have to be overall to get a negative 2? It's got to be 12, positive 12. So how do we get a positive 12 with 2 chromiums? Plus 6. So they're plus 6 each. Okay, I'm actually going to use some whiteout because I want to get rid of this stuff. Okay, that's good enough. So how do we use oxidation numbers? I'm going to show you that now. We look at oxidation numbers for a particular element and see how it has changed. So can you see for the chromium, it's gone from a plus 6 to a plus 3, which is a decrease in oxidation number. Here, the oxygen is minus 2. If we look over here, it's a minus 2, no change. So I'm not going to draw any arrow here. The tin is a plus 2, and here it's a plus 4. So the tin, the oxidation number has increased. And here the hydrogen is a +1, and here it's a +1, so no change. And here we have a -2 and a -2, so no change. So the elements where the oxidation number has changed is chromium and tin. And here's how you deal with these arrows. If the oxidation number decreases, we say that that element was reduced. And I like that because when an arrow goes down, decrease and reduce, those are synonyms, right? They mean the same thing. If it was reduced, it was rigged. And if it was rigged, it gained electrons. And it's the oxidizing agent. So if it was reduced, it's the oxidizing agent. Now, if the arrow goes up, that's an increase, and we call that oxidized. For oxidized, you use oil rig. Oil starts with O, matches oxidized. Rig starts with R, matches reduced. G is for gain electrons, and you can probably guess what L stands for, lose electrons. And if you're oxidized, you're the reducing agent. So normally, instead of writing these here, I would write them right next to the arrow on this particular line. So you can see that this chromium is reduced. It's rigged, which means it gains electrons. And it's the oxidizing agent. And on the bottom, we have oxidized, loses electrons. Notice 1O for lose, and it's the reducing agent. Any questions here? Okay, we may skip this one and go to, I want to see if we have another one where there's a redox reaction. Before we do this one here, actually, let's do this one here. Then we're going to jump to this one, and that'll be it. Because it's already 7 o'clock. All right, so let's do this one here. So our first rule is pure elements that are neutral. I don't see any. So our next rule is monoatomic ions. So I'm not going to rewrite this equation, but clearly that's a monoatomic ion. So this is a +3. Here we actually have 2 monoatomic ions. The sulfur is a sulfide ion, -2, and the iron is a +2. Okay, so now that we've applied the ion rule, we now look at fluorines, hydrogens, then oxygens. Here's some hydrogens, they're +1. Here's some hydrogens, they're +1. Now for this H3O, these oxidation numbers have to add up to +1. So I think it's clear that the oxygen has to be a -2 for that to work out. And that's nice because we want those oxygens to be -2. Okay, so here's another oxygen, that's a -2. Here's another oxygen, that's a -2. And here's another oxygen, that's a -2. So what does the oxidation number on this nitrogen have to be if you have 3 oxygens with a -2, and altogether the nitrogen and the 3 oxygens has to equal a -1? And the answer is +5. Here, when you have 1 nitrogen and 1 oxygen and it has to add up to 0 charge, it's pretty obvious that the nitrogen has to be +2. +2 and -2 is 0. This sulfur is going to have to be a +6. And now we've assigned all the oxidation numbers. Now, the interesting thing about this, and I'm going to get rid of this down here, is the following. If we look at iron, iron goes from a 2 to a 3. Is that an increase or a decrease? Well, that's an increase. Sulfur goes from a -2 to a +6, also an increase. Nitrogen goes from a +5 to a +2, which is a decrease. Oxygen goes from a -2. Well, we don't know whether this ends up here or this ends up here, but regardless, it ends up being a -2, so it doesn't change. This oxygen also doesn't change. This hydrogen doesn't change. So we actually have 3 things changing. I always like to start with the arrow going down first. Let me line these up again. Oh, there it is. I was saying, this doesn't make sense. Because it's this problem. So I like to start with the arrow going down, because down means decrease, which means reduced. What goes with reduced? Oil or rig? Well, rig. What does G mean? It means gains electrons. And what type of agent is this? It's an oxidizing agent. And for the arrows that go up, oxidized, oil, loses electrons, and it's the reducing agent. And it turns out that the iron is also oxidized. It's oiled, it loses electrons, and it's the reducing agent. So we have 2 reducing agents in this particular problem. Any questions on this second one? Okay, so I wanted to jump to this problem here. Identify each of the following as a oxidizing or reducing agent. So let me show you how to tackle this. And I'm going to skip this HNO3 and I'm going to go straight to sodium. Now, what do we know about sodium? Sodium likes to be a sodium ion. So what is the oxidation of a pure neutral element? 0. What's the oxidation number of a monoatomic ion? The charge on the ion. So the oxidation number of sodium goes from 0 to +1, which is an increase, which means oxidized, which means oil, which means loses electrons. And because it's oxidized, it's a reducing agent. So anything that likes to become a cation is probably a reducing agent. What things like to become cations? And the answer is all of this stuff likes to become cations. So all of these guys are reducing agents. Now, we're not going to include hydrogen in that. That's a little different. Let's look at Cl2. We know that chlorine actually likes to be chloride ion. Here we have neutral elemental chlorine, so it's a 0 each. Here it's a -1 each, and the oxidation number decreases. Decreases means reduced. Reduced means Rig. Rig means gain electrons. And if it's reduced, it's the oxidizing agent. So in general, nonmetals, which like to become anions, are oxidizing agents. So if we look at this list here, which ones are reducing agents and which ones are oxidizing agents? Well, for reducing, we have metals. So it's going to be sodium. For oxidizing, we have nonmetals. Now that says mental. So that's going to be chlorine and oxygen. Imagine that. Oxygen is an oxidizing agent. Now, what do we do about these two? Well, I'm going to show you that the MnO4, usually when you have these oxoanions or oxyanions, these are usually oxidizing agents. Okay, so these tend to be oxidizing agents. Now, what about acids? In acids, what often happens is these hydrogens become H2. So what's the oxidation number of a hydrogen in H2? It's 0. A hydrogen in HNO3 is a +1. So this guy decreases. And that means it's reduced. It's rigged. It gains electrons. And it's an oxidizing agent. So under oxidizing agents, not only do we have nonmetals, but we have acids. And these oxoanions. And that's how you do a problem like that. You ultimately look at how the oxidation number changes. Now, the rest of these problems in this particular set, the ones I skipped over, and these at the end here, you'll find these in the other videos also. Okay? All right, folks, thanks for attending. Hopefully I'll see you tomorrow. Tomorrow we're going to be starting chapter 4, and we're going to be doing a lab where you don't have to do anything, you just have to watch a video. Well, I shouldn't say you don't have to do anything. You have to watch a video, do some calculations, and answer some questions.
Nice.
So it's an interesting thing to watch. All right. Have a good evening, people.
Later, Tony.